It is Friday, April 2nd. We're going to take a look at the UDP Offload Engine demonstrator. So this shows the implemented design of the 4 UDP offload engines that are present on the uoeX example design. We can take a peek to see what area they use by expanding the subsystems here. We see we have a 8-byte, a 16-byte, a 32-byte, and a 64-byte design. You can see all the designs are in the center SLR of the 3 SLRs in this VU9P device. This happens to be on a VCU118, but it could just as well be on a U200. Let's zoom in on that center SLR. Just to get an idea of area, let's highlight the 8-byte design in this default color. Let's highlight the 16-byte design in this color. Let's highlight the 32-byte design in this color. And last but not least, let's highlight the 64-byte design in this cyan-ish color. So each one of these different colored blocks here represents a different UDP offload engine, along with its packet generators and checkers, I should say as well. We'll get more on that in a moment. Each one of these systems is identical except for the parametric setting of the width of their data path. Let's just pick in this 8 one to start and open that up. So we can see that there are 4 blocks in each of these 4 systems. There's a UDP offload engine, which is the IP core that converts layer 4 datagrams into layer 2 frames. There's a datagram generator here that generates datagrams. There's a datagram checker that checks datagrams. There's an L3 loopback adapter, which is used for some peculiarities of the test. And probably most important, or quite important, we'll zoom in here on the UOE block. You can see that there's a connection from the Mac TX that we're connecting right back around to the Mac RX. So in this example, the datagram generators are generating datagrams. They're converted into L2 frames. The L2 frames then come back in, and then the datagrams are checked. So we're going all the way through. This is similar to doing a Mac PCS or media loopback. There's the VU9P device on the VCU118 to program the bitstream. We'll simply program the device. There are no ILAs in this design, so there's no probe file. On completion of loading the bitstream, all of the 8 user LEDs will be extinguished except for the leftmost LED number 7, which will blink. We'll CD down into the directory system console. And here we'll say make server. And what you'll note is after running make server, a number will come up where it says connect XSDB server to use, this is the name of the machine, but you want to pay attention to this number here, 41611. This command will sweep various message sizes over powers of 2 over the 64, 32, 16, and 8-byte cores in sequence. So if we run it, we'll start with the 32-byte core, and notice that for small message sizes of 64 bytes, we're down at about 15 gigabits per second. But as soon as the message size comes up to 256 bytes, we're now up to 61 gigabits a second. At 512 bytes, we're up to about 98 gigabits per second, and once we get over a kilobyte message, we're safely over 100 gigabits per second, actually well exceeding the 100 gigabit Ethernet line rate because we're not limited by it here in our direct L2 loopback. Now here we've started the same sweep again, this time using the 32-byte core, half the area, so we wouldn't expect to get quite as quick. We start out at about, for 64 bytes, at about 15 gigabits. At 128, we come up to 30. At 256, we come up to 45. And then you can see by the time we get to 512, we're flattening out here at about 56, 57 gigabits per second, for the 32-byte core. Now here with the 16-byte core, similarly for 64 bytes, we're down here at about 15 gigabits per second. And very quickly we come up to our plateau of about 27 or 30 gigabits per second or 29 gigabits per second as the packet size gets larger and larger. Last but not least, we'll sweep over the smallest core, the 8-byte core, and we see that our performance for a small packet on the 8-byte core is down at around 6 gigabits per second, increasing to 10 for 128-byte messages, increasing to 12 gigabits for 256-byte messages, and finally plateauing off around 14 gigabits per second for 512-byte messages and beyond.